Welcome to EDUCARE. Today, the short circuit test of transformer will be explained. After go through the full tutorial, I am sure that you will have a clear concept about the short circuit test of transformer. Still, if you have any doubts, please write down in the comments box. This is a transformer under short circuit test. The rating of the transformer is a 10 kVA by 2 kV by 100 volt transformer. Therefore, the rated HV current IH equal to 10 divided by 2 equal to 5 ampere, and LV rated current equal to 10 into 10 to the power 3 divided by 100, that is equal to 100 ampere. Now, in the short circuit test, the one of the winding is short circuited. Suppose this is the HV winding and this is the LV winding. I will short circuit the LV winding through a thick copper wire, and we will vary the transformer until the ammeter show the rated current. What is the rated current of HV? The HV rated current is 5 ampere. That means when the ammeter indicates 5 ampere, then I will take all the meter readings. Now, the short circuit test can be performed in HV side or LV side. In the both cases, the wattmeter reading will be the same. But if we prefer this one, that means the short circuit test is performed in the LV side and HV is short circuited here. Then I have to vary the transformer until the ammeter indicates the rated LV current. Here the 100 ampere is the rated LV current. Therefore, when the ammeter indicates the 100 ampere, then only all the meter readings will be taken. Now, here by applying only 5 ampere, I am getting the required result. But if I do in this method, I have to circulate the 100 ampere current. Therefore, we will prefer this method. I will not prefer this method. That means the short circuit test is performed in HV side and LV side is short circuited. It is not performed in LV side by short circuiting the HV side. To conduct the short circuit test, the following meters are required. Number 1, wattmeter. I required a wattmeter since in the short circuit test the power factor is near unity, therefore the wattmeter will be the unity power factor. Next, I required a ammeter. In the ammeter, the rated HV current passes. Therefore, the range of the ammeter is the rated HV current range. Number 3, I required a voltmeter. In the short circuit test, the low voltage is applied. Therefore, I need a low range voltmeter. From the short circuit test, the following parameters are determined. Number 1, full load copper loss. Number 2, series branch parameter. That is equal to R01 X01. Number 3, the percentage of R and percentage of X. Number 4, the regulation of transformer is also determined from the short circuit test. In the short circuit test, the auto transformer is varied until the ammeter indicate the rated HV current, that is equal to 5 ampere, and at this instant all the meter readings are taken. Let the wattmeter reading is W of SC, voltmeter reading is V of SC, and ammeter reading I of SC. First, full load copper loss determination. Here in this case, ammeter reading I of SC is the rated HV current, and voltmeter reading V of SC is only 5 to 10% of HV voltage. And wattmeter reading W of SC is the full load copper loss plus of iron loss. Now the iron loss depends upon the voltage and copper loss depends upon the current. Here the voltage is only 5 to 10% and current is a rated current. Therefore, the iron loss is very small. You can neglect this one. Therefore, wattmeter reading I can say is approximately equal to full load copper loss. Point number 2, you have to find out series branch parameter. Let's draw the equivalent circuit of transformer at short circuit test. Suppose this is a resistance R01, reactance X01, and this is the high voltage winding. This is a low voltage winding. This is high voltage, low voltage. Low voltage winding is short circuited. Now the voltmeter reading is V of SC and the ammeter reading is I of SC. Here R01 is the equivalent resistance of transformer with respect to HV side, and X01 is the equivalent reactance with respect to HV side. Now the wattmeter reading W of SC is the full load copper loss, that is equal to I square R loss. Here current is the I of SC square into resistance is the R01. Therefore, I can write down resistance R01 is the W of SC divided by I of SC square, that is equal to wattmeter reading divided by ammeter reading square. Therefore, can I write down the wattmeter reading divided by ammeter reading, that is square, gives you the resistance of the transformer referred to the HV side. Again, the impedance Z01 is the voltmeter by ammeter, V of SC by I of SC, that is the voltmeter reading divided by ammeter reading. That means the voltmeter reading divided by ammeter reading gives you impedance of the transformer Z01. Once I know the resistance and impedance, I can easily find out reactance X01 is equal to the Z01 square minus of R01 the square. Therefore, I know R01, I know X01. Since branch parameter can be easily calculated. Now, point number 3, you have to measure the percentage of R and percentage of X of the transformer from short circuit test. Here, percentage of R is given by I of SC a square into R01 divided by E1 I1 rated into 100%. The percentage of R and percentage of X has been explained in the equivalent circuit of transformer. Link will be given to the description box. Please go through the video if you have any doubts. Here I of SC the square into R01 is the wattmeter reading, and this is the VA E1 I1 is the VA rating of the transformer. Into 100%. Therefore, I can say the percentage of R can be calculated as wattmeter reading divided by VA rating of the transformer. Which is obtained from nameplate of the transformer. Into 100%. This is your percentage of R. Z01 impedance equal to the voltage by current V of SC divided by I of SC. Therefore, V of SC equal to Z01 into I of SC. Again, percentage of Z is given by I of SC into Z01 divided by E1 into 100%. Here, the I of SC into Z01 is the V of SC divided by E1 into 100%. The percentage of Z will be given by, this is the voltmeter reading, V of SC is the voltmeter reading, divided by E1 is the rated HV voltage, which is again obtained from the nameplate into 100%. Once I know percentage of Z and percentage of R, then I can easily find out percentage of X is the root over of percentage of Z R square minus of percentage of R square. Therefore, I know percentage of R, percentage of X and percentage of Z. Now we have to find out the voltage regulation from the short circuit test. First, we draw the equivalent circuit of the transformer at short circuit test. This is the resistance R01, reactance X01, voltage V of SC, current I of SC. Now, this is the, if I draw the impedance triangle of the transformer R01, X01 this is Z01, this is theta of SC. Here theta of SC is the short circuit power factor angle of the transformers. Now percentage of R into cos theta 2 plus percentage of X into sin theta 2 gives you the percentage of regulation. This formula will be derived in the regulation chapter of the transformer. The syllabus have not been completed. In the next video, I will derive this formula. Now here theta 2 is equal to the theta of SC, short circuit power factor angle, and from this impedance triangle I can say cos of SC equal to R01 divided by Z01, and this value is approximately 0.5 to 0.6 lagging. From the previous step I know the percentage of R and percentage of X, and I know the theta 2 using this equation. Therefore I can easily find out percentage of regulation of the transformer. Let us practice a numerical. A single phase transformer has no load loss of 64 watt as obtained from open circuit test, and when a short circuit test is performed on its 90% of its rated current following in its both LV and HV winding, it measured loss is 81 watt. The transformer has a maximum efficiency when operated at which percentage of current, rated current. In the efficiency chapter, I have learned at maximum efficiency, the percentage of loading, that is equal to X, is given by root over of iron loss divided by full load copper loss. Already you have derived this formula in the efficiency chapter. Please go through that video, link will be given in the description box. Here the open circuit test, the loss is 64 watt. In the open circuit test class we have seen, in the open circuit test the iron loss is calculated. Again, if you have any doubt, go through the open circuit test class, link will be given in the description again. Therefore the open circuit test loss is the iron loss equal to the 64 watt, and in the short circuit test the loss is 81 watt. In the short circuit test the copper loss is neglected, but here the current is 91% of rated current. Therefore copper loss at 90% of full load is equal to the 81 watt. All of you know that copper loss at Y of full load equal to the Y square into full load copper loss. This formula has been derived in the copper loss chapter. Okay, please go through that video also. Here copper loss at 90% of full load is the 81 watt. Therefore this is 81, and Y equal to percentage of loading. Here 90% load has been given. Therefore this is equal to 0.9 R square into full load copper loss. From there I can easily calculate the full load copper loss is equal to the 100 watt. Therefore, at maximum efficiency, X equal to root over of iron loss equal to 64 watt divided by full load copper loss equal to the 100 watt. That is equal to 80%. Therefore, 80% of loading rated current, the transformer gives maximum efficiency. Option C is the correct option. Here let's practice another numerical. Get 2008 questions. It is desired to measure parameter of a 230 volt by 115 volt 2 kVA single phase transformer. The following wattmeters are available in the laboratory: W1, W2, W3, W4. The wattmeters used in open circuit and short circuit test of the transformer will be respectively. That means which wattmeter is used for open circuit test and which wattmeter is used for short circuit test. First starts 2 kVA transformer and the 230 volt by 115 volt. This is the HV and this is the LV. Therefore, HV current I of H equal to rating 2000 divided by 230, it is approximately 8.6 ampere current, and LV current I of L is the 2000 divided by 115, 2000, it is approximately 17.39 ampere. Now, in the open circuit test, the power factor is very less. Power factor is approximately 0.1 to 0.2 lagging. Therefore, for open circuit test, low power factor meter is used, either W1 or W2 for open circuit test. In the short circuit test, the power factor is near unity. It may be 0.5 to 0.6 lagging. Therefore, high power factor wattmeter is used in short circuit test. Therefore, either W3 or W4 will be used into the short circuit test. Here in the open circuit test, the rated LV voltage is applied 115 volt. 115 volt can be measured by W1 also or W2 also. Here the current IL at no load is very small, approximately 4 to 5% of rated current of 17.39 ampere. Since the current is very small, I need a small rating range of ammeter. Therefore, here ammeter is the 10 ampere, here ammeter is the 5 ampere. Since the current is very less, I require a low rating ammeter. W2 is the correct option. Here in the short circuit test, either W3 or W4. In the short circuit test, I know the rated HV current is passes. That means the current will be the 8.6 ampere. This 8.6 ampere current cannot be measured with the 5 ampere range. It can be easily measured by 10 ampere range. Therefore, W3 is used for short circuit test. This is for open circuit, this is for short circuit. That means W2 and W3. Option D is the correct option.